Alright, grade 12 chemistry. It's the last video of organic chemistry for us. We're going to run through our last two functional groups, which are amines and amides, and it's going to be all about polymers. So we're going to talk about an intro to polymers, talk about natural and artificial polymers, a little side trip into crosslinks. We'll talk about addition versus condensation polymers, and then some environmental issues of plastics. So a lot of practical organic chemistry is going to be happening in this video. I'm going to take that away, and let's get right into it with amines and amides. These are the only two that we're going to learn that have nitrogen in them. Amines, you can kind of think of them as like the alcohol version of nitrogen, the nitrogen version of alcohol rather. So this is just ammonia. That is not an organic compound, but if you've got carbon attached to something with a nitrogen, that becomes an amine. The word comes from the same as ammonia. This is a primary amine when there's just one carbon and two hydrogens hanging off. When we want to draw that, I'm just going to erase some of this stuff here. When we draw an amine, we follow the same heteroatom rules as we normally have been. So if we have a primary amine, we have to write NH2 like that. If the amine's on the other end, maybe it's doing something like this, the nitrogen has to be the thing bonded to the carbon so that it's still an amine. So we have to write H2N like that. So that's a primary amine. That's still a primary amine because the nitrogen has two hydrogens and one carbon group on it. A secondary amine would have two carbon groups hanging onto the nitrogen. So if I came over here and let's say I took away one of these, let's make something like this, right, with a hydrogen on it. Or here, if it was over here, I might do something like this, and then there's a hydrogen here. Those are secondary amines. And then there's the tertiary amine. The tertiary amine actually has no hydrogens at all, which is important because it changes its properties, right? Now this thing can't hydrogen bond. If we did something like that, or if we did something like, I don't know, let's throw a phenyl group on there just because I feel like it. That's called aniline. It's a amine with a phenyl group on it. Yeah, so that's amines, primary, secondary, tertiary. When we name them, they're obviously named with amine. They're called amine at the end. Like here's ethylamine, dimethylamine, ethyl dimethylamine, butylamine, ethanolamine, so ethanolamine. So that's one way to do it. You can also, but the official way is here in brackets, methylamine, N-propylamine. N-propylamine, that's actually one word together. Isopropylamine, or you can call it propan-2-amine, sorry, propan-1-amine. Methanamine. So this is the actual the actual IUPAC method is these big ones up here. N-methylethanamine. So notice the N. This is new. N, because the nitrogen doesn't get a number, we just give it a capital N. So this N means that the methyl is on the nitrogen. If there's two things on the nitrogen, if this is a tertiary amine, it has an N-ethyl, N-methyl, and then propanamine. So it's a propanamine because it's the longest chain, 1, 2, 3. Then on N we have an ethyl, and on N we have a methyl, and that's just going to be alphabetical like we're used to. We're going to stick to these simple amines and we're going to use the simple rules. But here's an example of a tough one. You've got 3 propyl groups on this amine, but this propyl group has the chlorine on 1, this propyl group has the chlorine on 2, and this propyl group has the chlorine on 3. And so you get these kind of complicated names where you have to get into the brackets, or you can use the prime system where you've got 1 is your main chain, 2' is a secondary chain on your nitrogen, and 3' is a tertiary chain on your nitrogen. That's another way to do it. Or you can do this like 1 chloro is there, N, and then 2 chloropropyl because that's propyl on 2 with chloro on 2, and N, 3 chloropropyl, so those are on N. We got those brackets and they're on N. So official IUPAC way to name this thing. I'm not going to give you anything that crazy for amines, but yeah, that's amines. Don't worry too much about making an amine. They're just going to exist. Let's talk about amides. When you have an amine, as long as that amine has a hydrogen on it, you create and you meet a carboxylic acid, and you meet an amine, you form an amide. It's a condensation reaction. So butanoic acid meets methanamine. This hydrogen, this hydroxide is going to go, and this blue hydrogen is going to relieve the nitrogen. So remember, condensation is going to get rid of water. There's the water going away, but the bridge now is a nitrogen bridge. So you can think of an amide as like an ester, but with a nitrogen bridge instead of an oxygen bridge. So it's a nitrogen, and then the double bond to oxygen from the carbon still exists. So you know which. So just like in an ester, you know which side came from the acid, and you know which side came from the amine. And just like an ester, they're named like that too. We name the primary chain the one that came off of the acid. They're named for the acid. So this is butanamide. That's the butane, 1, 2, 3, 4, amide. And on the other side, we have on N, notice N-methyl. N-methyl. So the N side of things just becomes a side chain, like we named amines earlier. And it gets this amide ending. In terms of priority, they are below esters. So yeah, they're like esters. One thing to note is that tertiary amines won't form amides because there's no hydrogen to lose. A tertiary, you need to lose that hydrogen to make the water, so a tertiary amine won't make an amide. But you can make primary, secondary, and tertiary amides, right? If X and X is anything that isn't a carbon group. So this would be like ammonia reacting with a carboxylic acid, and you'd end up with a primary amide. This would be a primary amine reacting with a carboxylic acid. You end up with a secondary amide, and this would be a secondary amine reacting with a carboxylic acid. You get a tertiary amide. Let's do one of these just for fun. Let's take an amine. I'm gonna do, I don't know. Let's choose an amine. How about this one here? Right. That is, 1-methylethanamine, or you could call it isopropylamine. And we're going to connect it to this carboxylic acid. Let's make it. That looks good. Propanoic acid. Right. We're going to connect them together. We're going to add them together. We need to lose a water. We're going to lose this OH for sure, and we're going to lose one of our hydrogens. One of our two hydrogens is going to go to make H2O, right, in our condensation reaction. So this is going to make, we're going to have this here. It's still going to be attached to the nitrogen. We're going to have one hydrogen left over because we only needed one of these hydrogens to make the H2O. The other H came from here. And that's going to make a bridge to our double bond oxygen. And there we go. And there is an amide that we've made. To name this thing, this side, right? This side had the acid, so it's going to be a propanamide. Propanamide. And then on N, what do we have on N here? Well, you could call it isopropyl because that's what it is, but we haven't learned isopropyl. It's a common side chain that we can use. But you can call it 1-methyl ethyl. 1-methyl ethyl. And 1-methyl ethyl propanamide if you wanted to. But that's how we name these things. So we name amides. Alright, so that's amides and amines. Let's talk about properties real quick. We're talking about naming amides. So yeah, they're named for the carboxylic acid, so we already covered that. Right, here's N-diethyl ethanamide. Same kind of idea. You can have N-ethyl, N-methyl. You can do whatever you want there. Right. So properties. Both of them can hydrogen bond as long as they have a hydrogen on the nitrogen. So that gives them a higher boiling point than, say, an ester or an ether. If they're tertiary, though, they're going to go right back down in terms of boiling point because there's no hydrogen bonding. Small ones are soluble in water, like esters, aldehydes, and ketones. It's very, very important for life. Right? Here's an amino acid. There's an amino on one side and an acid on the other, and that lets them actually chain together, acid to amino. Right? And you make an amide group. This green thing is an amide. There's a nitrogen bridge and a carbon with a double bond oxygen. All proteins are made this way. All of our proteins in our body, and proteins do everything in our body. Grade 12 biology, we talk your ear off about proteins. So that's an amide bond. We call it a peptide bond in biology, but it's an amide. That's peptide synthesis. So that is making an amide bond from a carboxylic acid on one side and an amine on the other. There's the amine on the other side. Next up we're going to talk about polymers. Proteins are polymers. So I'm going to pause and we'll get the polymer thing set up. Right, so let's look at this amino acid. We have an amide on one side and a carboxylic acid on the other. The carboxylic acid is going to meet up with the amide and make this amine and make this amide bond, but there's still a carboxylic acid here on this side. Hang on, still a carboxylic acid on this side here, which means that could bond to another amine group, and then you'll have another carboxylic acid, and so on and so forth. So that's going to create this big long chain, and we would love to be able to do this artificially, and we can. We can do that with something like this. This is diaminohexane, or 1,6-hexyl, what it would be. Diaminohexane is the way it's normally called. And this is hexanoic diacid, because it's two acids. When we put these together, we still have an amine on one side and an acid on the other. We can build the chain with a bunch of condensation reactions. Make a big long chain of amides. Amide, 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 amide. You get this big long chain of acid, amide, acid, amide, acid, amide that we've condensed together. Of acid amine that we've condensed together. This is called polymerization because we've made many things, many MERS. Anything from this is called a polymer, and there's actually a great video of this. I'll have this linked in the description. This is actually my chemistry professor from university, Dr. Bob Burke at Carleton University. He's going to mix the two, the diethylamine and the diacid, hexane diamine and the diacid, and he reaches in, and he's going to pull out the polymer, the big long chain, and it just keeps going. It just keeps going, keeps going, keeps going, keeps going. So yeah, please watch that down below. It's very, very cool as a video. So yeah, it's making these big long chains. So he's making nylon. That is nylon 6,6. So nylon's a polymer. You probably have some clothes that have it, or maybe rope that's made out of nylon. So polymers. Polymers are made out of monomers. A monomer is the individual thing. So here's a monomer, ethene. When we chain them together, this is actually an addition polymer. The double bond breaks, leaving room for two bonds on each side, and you can put together polyethene or polyethylene. That is the type of polymer that's in plastic bags, like those plastic shopping bags. The single-use ones. The individual compound is the monomer. So here's another example. Here's polystyrene, which is what makes styrofoam. This is styrene. Styrene is just one of these. And it's also an addition, so that it's a double bond's going to break. You're going to make room for another bond between these carbons. You end up with polystyrene, many styrenes. Many styrenes. So monomer and polymer is important. This is called a homopolymer because everything is the same. It's just ethene, 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 ethene. That is a homopolymer. The other option is a copolymer. A copolymer. If you have more than one monomer, you end up with a copolymer. So example, nylon is a copolymer because you got the diamine and the diacid, and they chain together. So is DNA. You have different nucleotides to chain together. So it's a copolymer. Proteins are copolymers. Lots of things are copolymers. All right, we're getting into some natural polymers and crosslinks. So natural polymers. Right. Here's a natural polymer. It's glucose. Glucose having an OH and an OH can link together. All of these OHs can link together. Two alcohol groups, right? They link together. They make an ether. Essentially, these are just big, long ether groups. And you can chain glucose to glucose to glucose and make these big, long chains of glucose. Starch is one of these things. This is why starch carries lots of calories, right? It's just glucose. Your body can use it to carve glucoses off of it. Glycogen, same thing. Your body actually uses that to store energy. And also cellulose, the one that is in cell walls, is glucose, but it's in a different arrangement, and your body can't break it up. So that one doesn't actually give you any energy, even though it's completely made out of glucose. Wood is glucose, which is always interesting to me. But they're all glucose homopolymers, because it's just glucose, 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 glucose. Other ones, copolymers, like keratin. Keratin's our skin and our nails and stuff. Wool, skin, feathers, horns. It's a big, long chain. Notice these little hydrogen bonds in here, these red hydrogen bonds. It's hydrogen bonding to itself. And it makes it very tough. Makes it curl around itself, and it's packed into these cells that die, but the keratin sticks around. And so it makes this tough stuff that we call hair and skin and nails, and feathers and stuff. Fish scales too. Here's rubber. This is what rubber looks like. Rubber. It's got these double bonds in it, and it's actually what makes it stretchy, because those double bonds have a certain amount of, like, the way that the double bonds are held like this, they have a certain amount of give. And so combined with a bunch of bonds all in a row, you get this stretchiness to the rubber. It's very cool. And this is the monomer. The monomer is isoprene, or 2-methylbute-1,3-diene. And you can kind of tell that the double bond will break and make room for the next bond in the series. So that's rubber. It's also a natural polymer. Now we're getting into artificial polymers. So there's kind of a little bit of history here, but it's more about what the polymers look like. Artificial polymers. Here's the first kind of synthetic polymer. This is rubber, but it's just one long chain, and it's just one long chain. Because it's one long chain, the chains don't really have any reason to stick next to each other. So old rubber tires would fall apart very, very quickly, because even though the chains were very long, the only thing holding them together was like van der Waals forces, right? Like London dispersion forces. Until this guy, Charles Goodyear, accidentally heated up some rubber with some sulfur, and it made these sulfur bridges across his rubber. Of course, he didn't really know that, the chemistry of the cross bridge, but it worked. And it made this tough, flexible rubber, and from then on, they vulcanized rubber, adding these sulfur crosslinks. So that turned it from a chain into a net. And now that it's a net, right, it's got all these crosslinks, it's much tougher, much stronger, much more resistant to damage. And so crosslinks makes strength. So a lot of plastics that we have now are cross-linked between themselves to get lots and lots of strength. I've heard that crosslinks are also the reason that curly hair is curly, because the keratin makes crosslinks. I'm not qualified to talk about that one, but yeah, maybe look into that. Then we got into fully synthetic polymers, right? Here's the first one. It's bakelite. And it was phenol and formaldehyde, two very easily accessible starting materials. It was processed and it turned into bakelite. So this is a copolymer, and it's this cool kind of addition polymer, but it like loses the double bond as it adds. The oxygen gets taken away as it adds together, and it's kind of like a condensation. Bakelite was really interesting. They made jewelry out of it. They made phones out of it. They made all kinds of interesting things out of it. And they people collect it now. It's actually a collectible. I had a student one year actually bring in some Bakelite jewelry, and it was really cool to see this first fully synthetic plastic. Other people say that vinyl was the first synthetic plastic, or but yeah, you can talk about that too. That was a guy that was trying to invent artificial billiard balls because ivory was getting too expensive, so they wanted to make cue balls out of not ivory. World War II, they worked out synthetic rubber, so styrene and butadiene. You got this styrene butadiene rubber, which worked pretty well for cars and trucks and things. They needed to make lots and lots of cars and trucks, and rubber trees, only make so much rubber, so they were able to chemically make rubber. And then plastics just took off, like in the 50s and 60s and 70s. Plastics were huge business back then. If you were a plastic chemist, you were making a lot of money. They were like the rocket scientists of their day. I guess they were also rocket scientists of their day, because that was when Apollo was going on. But anyway, plastic scientists were making the big bucks back then. Now we're into our next section, which is addition versus condensation polymers. So I'm going to pause. So there are two classes of polymers, two other classes of polymers. There's addition polymers and condensation polymers, and it has to do with how we chain the individual pieces together. So if you remember addition reactions from earlier, ethylene, right, and bromine together, what would happen is the double bond would break, the second bond would break, and then you have space to install your two bromines. That's an addition reaction. In a condensation reaction, you are removing water and you leave behind this bridge, an oxygen or a nitrogen bridge, right? These bridges. So here's an amide getting formed, and you leave a nitrogen bridge. Here's an ester being formed, you leave that oxygen bridge. There's the oxygen. So you can kind of tell the difference. Addition reactions require a double bond. Condensation reactions require some kind of way to get water out of there. So you'll need an OH group on one thing and a free hydrogen on the other thing. So let's talk about addition polymers. This is isoprene. When isoprene gets together with other isoprene molecules, that's how rubber is made. That's how natural rubber is made. And it can be kind of hard to understand this structure, how this structure comes about from this structure. But it might help if we draw it. So let me draw it. We have this molecule. This is isoprene. We'll put it there. And then we'll have a second isoprene, which we'll draw like this. There's a second isoprene. Put a third isoprene here too. Why not? Like this. Right, we'll put a third isoprene. And then we have to think about, how do addition reactions work? How are we going to add these together? Well, the way all addition reactions work is we break the double bond. We break the double bond. Right? We break the double bond. And we install a new bond. Right? We install a new bond. We break the double bond. We install a new bond. Right? We break the double bond, we install a new bond, we break the double bond, we install a new bond. So what you end up with is you have this double bond up and down. This is still there, right? That was there before. That single bond was still there before. But the new bond, right, the new green bond is now attached to this guy. Right? That guy didn't get affected. And then the same thing happens here. That bond, one of the bonds broke, but the other one didn't. We have the new double bond. That's attached to this guy that didn't get affected. And so on and so forth. Right? This just keeps going. And you get rubber. So that's an addition reaction. We're breaking a double bond to install new things. When we have double bonds, we can make a chain of addition reactions. We just need one double bond per molecule that we're adding. So that's rubber. Here's a synthetic one, right? Ethene. You can just kind of imagine these. The double bond just kind of migrates over almost to make single bonds between all the molecules. This is still called polyethene, even though there's no double bonds in it, because it came from individual ethenes. Right? Distinctive property here is that it's all carbon-carbon bonds, just carbon, 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 carbon. The other type of polymer is condensation polymer. Those ones are created by condensation reactions. Right? So proteins are an example of a natural condensation polymer. Glucose makes a bunch of ethers, right? Glycosidic linkage. And so a lot of artificial or natural polymers are condensation polymers. Here's nylon. Nylon is we already covered it, but it's an amine and a carboxylic acid, so you get this polyamide. You can get polyesters, various polyesters. Like my shirt has polyester in it. Polyesters. You get polyacetals as well, which are like polyethers. So like the stuff that's on like backpack clips or guitar picks, anything that needs a little bit of flexibility but still be tough, kind of thing. It's made of this stuff, polyoxymethylene. Your typical PET bottle, polyethylene terephthalate, which is always a fun word to say, is made out of a polyester. Nylon's made out of a polyamide. How do you tell them apart? How do you tell addition versus condensation? It's those bridges. You can easily see them by identifying the repeating chains, and you see those bridges, the nitrogen bridges, the oxygen bridges here. These have no such thing. Right? They don't have those bridges along the way. They might have oxygens kind of hanging out, up and down, but if they're not part of the main link, it was an addition polymer rather than a condensation polymer. So that's addition versus condensation polymers. Right. Last piece here is an environmental issue. Environmental issues. And the environmental issue really boils down to one thing and one thing only. It says plastics are new. Evolution is slow. Right? Plastics are new and evolution is slow. We have this brand new thing that appeared on the planet starting about 75 years ago. And it takes a while for things to figure out how to eat things. And so basically nothing's figured out how to eat plastic. This is good for certain things, like I wouldn't want something to eat my pen, which is made out of plastic. I wouldn't want something to eat, most of my car and stuff like that. But it's bad for other things, like those shopping bags that we all use and things like that. So that's where non-biodegradable comes in, right? Biodegradable means something in the environment has to be able to eat the thing. It does lead to other problems like the Pacific garbage patch. Basically, plastics can't get eaten, but they can get shredded. So like sunlight can come and turn the plastics into tiny, 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 tiny versions of themselves, and you get these microplastics in the water. And it's extremely hard to deal with. They make a almost like a solution of tiny, tiny plastics, just a few atoms in the water, but it still can't be biologically degraded and recycled into the environment. The carbon cycle is stopped there. And we just keep on putting more and more of it into the environment, so that's an issue. Especially bad for addition polymers, because those carbon-carbon, long carbon-carbon links, nothing's really worked out how to deal with those yet. Easier for condensation polymers because condensation polymers like the glucose stuff, like the glucose chains, things know how to eat those now. And so and proteins, things know how to eat proteins. So if you have a condensation polymer, you're more likely to find something that can biodegrade it. And so this is where polymers like polylactic acid, things like that have come in to create biodegradable plastics, compostable plastics. You might have heard of those, like the coffee cup lids and stuff that are compostable are made out of these, typically made out of condensation polymers that can be eaten. One last piece here is thermoset versus thermoplastic. Thermoplastic Now the word plastic itself comes from to be able to bend. Bendy. Plastic means bend or flexible, I think. And we have these two classes of them. We have thermoplastics and thermoset plastics. The difference is thermoplastic gets bendy under heat. Thermoplastic, heat bendy. Here's a great example of it. Here's and again, this video is going to be down in the description, but this is a heating coil, and there's a plastic sheet. He's going to put a plastic sheet on it. Right, plastic sheet. The heating coil is going to heat up the plastic, and now it's bendy, and you can bend it. Then while he waits for a bit, now it's bent. Right, look at that, thermoplastic. So thermoplastic, if you heat it up, you can make it change its shape, and now it's that, like that. This is really cool for stuff like vacuum forming. Right, vacuum forming, which I might actually just find a video of it. Here you go. Here's a vacuum forming machine. And here's how it works. You put the plastic on, it heats it up. You see the fan up there for the heating. Now it's heated. You turn on the vacuum, and the plastic forms to the thing. Right, and now you let it cool, and you've got the plastic. You've got the thing that you've made. Again, video is going to be down below. This is using ABS, a very common thermoplastic. Thermosets, on the other hand, are basically like a powder. They get injected hot, and when they're cold, that's it. They're not going to turn back into a bendable thing. They're just going to crumble, basically, afterwards. And the difference is crosslinks. So we talked about crosslinks before. Thermoset plastics typically make crosslinks as they cool. Thermoplastic ones typically don't. And here's that heat molding process, the vacuum forming process that involves heat. So here's the important concept. Here's a review. Homopolymer versus copolymer. The idea of one monomer versus several monomers. We have thermoset versus thermoplastic. And then recognizing addition and condensation polymers, being able to chain the addition and condensation polymers, and to talk about environmental effects of them, where addition are worse for the environment because they're too new, and condensation are typically better for the environment, but even then there are condensation polymers like nylon, like this microfiber cloth, which is polyester and nylon, both of which are condensation polymers, but they're not biodegradable. So it's not a be-all end-all, but most, it's more likely that a condensation polymer will be biodegradable. And we talk about the importance of crosslinks in plastics because it turns it into a net instead of a chain, makes it a lot stronger. Yeah, hey, that's it. That's the whole organic unit. Look at that. We'll maybe do some reaction practice. I might make a organic reactions video. And other than that's it for content. And yeah, study hard and good luck on the test.